Precalculus, Chapter 2, Lesson 2.3, Polynomial Functions and Their Graphs. Let's recall from before that a polynomial is a string of terms that are consistent of whole number exponents, so no decimal exponents, no fraction exponents, and no negative exponents, with real number coefficients. And examples of some not polynomials would include x squared plus x to the negative 2 power, x to the 1/3 power plus 2, and 2x cubed plus 2 over x. These are all not polynomials because they do not have those whole number exponents. One other thing we should mention here is that if we're dividing polynomials, we cannot have a variable in the denominator. An example of a polynomial would include if, for example, we did 10x cubed y minus 13x plus 2y squared, and then we could also do plus 7 there. Remember, it is okay to have multiple variables, again, as long as each of those variables only have whole number exponents. Polynomial functions of degree 2 or higher have graphs that must be smooth and continuous. By smooth, we mean that the graph contains only rounded curves with no sharp corners. And by continuous, we mean that graphs that have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So on the xy axis, you should be able to draw the graph in one fluid motion. We've also talked about the degree of a polynomial before. Remember, to find the degree of a polynomial in factored form, what we're going to do is add all the exponents to find the degree. For example, in this case, if we take all the factors, there's a total of 4 of them. And so 2x minus 3's, 1x minus 1 factor, and then 1x plus 3 factors. So if we add those all together, they would be degree 4. In the general form, it is always going to be the biggest exponent in the degree. This would be the same thing as if we multiplied the factored form all together, and we would end up with a degree 4 polynomial. One new thing we're going to talk about is the end behavior of a polynomial function. The end behavior is what's happening on the far left and the far right of the graph. Kind of think of this as the behavior of the arrows of the graph. And the behavior of the graph can always be predicted based on the degree, mainly if it's an odd degree, like 3, or an even degree, like, let's say, squared or to the 4th power. If it's an odd degree, say degree 3, this would be an example of, like, in this case, x cubed. This is where we're going to have opposite end behavior. So like in this case, if we think about the odd graph, so x cubed, the cubic graph, well, remember this is our S curve. And so notice how the left arrow is going down towards negative infinity or falling, and how the right arrow, or going to the right side, it's rising, going towards positive infinity. So if we contrast that with an even degree polynomial, let's say degree 2, so this would be our x squared graph, the quadratic. If we remember correctly, this looks like a parabola. Notice how the left arrow and the right arrow are both doing the exact same thing. And so they're both going up towards positive infinity. And so if we have an odd degree, our end behavior is going to be opposite. But if it's going to be an even degree function, they're going to do the exact same. We sum up finding the end behavior of a polynomial function by using the leading coefficient test. So the leading coefficient, remember, is the coefficient that is in front of the term that gives us the degree of the overall polynomial. So for example, if we have a positive leading coefficient and an even degree, this means that we're going to get that positive parabola, like an x squared. But remember, if we have a negative leading coefficient, what that's going to do is that negative a is going to, think about transformations, is going to flip that over the x-axis, making it go both down towards negative infinity. The odd degree is the same thing. If it's odd and has a positive leading coefficient, this will be that normal cubic shape of the S-curve with a fall to the left and a rise to the right. But then if we have a negative leading coefficient, it will flip over the x-axis, giving us a rise to the left and the fall to the right. Another way of writing the end behavior here would be for if it's a positive leading coefficient and an even degree, it would be a positive infinity, or a rise, rise. If we have an even degree with a negative leading coefficient, this will be a fall. If we have an odd degree and a positive leading coefficient, this would be a fall rise. And then if we have an odd degree and a negative leading coefficient, this would be a rise fall. We need to be able to use the leading coefficient test to help us with the behavior of the graph. Another aspect of graphing polynomial functions that we need to take into account is multiplicity. When we're talking about multiplicity, multiplicity is going to be defined as the number of times a particular zero or factor appears in a polynomial. So in this case, if we think about a zero, that's another way of saying solution, root, or x-intercept. If a factor has even multiplicity, then that means the graph is going to touch the x-axis at that x-intercept, kind of like how it does in a parabola. So for example, when we're talking about even multiplicity, well, in this case, if we take the polynomial x minus 2 squared, since it only appears 2 times, which is an even number, that means at x equal to 2 on the x-axis, it's going to touch the x-axis and just bounce right back. Compare that, though, to a factor that has odd multiplicity. This is where it's going to cross the x-axis. So for example, if we take the polynomial x minus 2 cubed, since the 3 is an odd number, then that means the graph is going to cross through the x-axis at that point. Regardless of whether the multiplicity of a zero is even or odd, the graph is going to tend to flatten out near zeros with multiplicity greater than 1. By flattening out, it's going to look like it's leveling off at that particular x-intercept. So knowing if the graph is going to cross or touch or flatten out at the x-intercepts helps us get the behavior of the graph and helps us draw it. So in our first example here, it says for us to find the zeros, which is another word for x-intercepts or solutions, to the polynomial -4 times the quantity x plus 1/2 squared times the quantity x minus 5 cubed. And we want to give the multiplicities of each zero. Then we want to state whether the graph is going to cross or touch the x-axis at each of those zeros. So the first thing we need to do here is find the actual zeros. And we can do that by setting the f of x equal to 0. And so if we set our equation equal to 0, we'll notice that this is already in our factored form. So this means here that then we can go ahead and set those factors each equal to 0. And if we do that, we're going to get x equal to -1/2 and x equal to a +5. So the +5 and the -1/2 are both going to be our zeros or our solutions. Since that -4 is just a coefficient, is a constant out there that we're just multiplying by, it's not going to have an effect on solving. The next thing we want to do here then is for each of those zeros, find out what actually is its behavior at the x-axis. Notice, since the x plus the 1/2 was squared, which is an even multiplicity, then that means it's going to touch the x-axis at -1/2. Similarly thing, if we look at the x minus 5 though, this was an odd multiplicity because we have x minus 5 cubed. So that means there's 3 x minus 5 factors. And so since it is a cube, that is an odd multiplicity, so that means it's going to cross the x-axis here. To illustrate this, let's actually look at the graph of this polynomial. So we said before that since the x plus 1/2 is squared, it's going to touch at the x-axis. But since the x minus 5 is cubed, which is an odd multiplicity, it's going to cross right through the x-axis. So this right here is what we call the behavior of those zeros. And we do that by finding the zeros and looking at their multiplicities. One other thing that we want to talk about here is the intermediate value theorem, sometimes called by mainly me the IVT. The intermediate value theorem says that if we take a polynomial function with real coefficients, then that means that if we evaluate two values, so f of a and f of b, and then those evaluated numbers have opposite signs, so one's positive, one's negative, then there must then at some point in between those two values, then it's going to be evaluated at 0. This is equivalent of saying that there must be one real root, or there's going to be an x-intercept between those two values. So let's illustrate this by showing that the polynomial function 3x cubed minus 10x plus 9 has a real zero between -3 and -2. Well, by the IVT, if we found that if we evaluate found f of -3 and f of -2, and they have opposite signs, then that means that a value between -3 and -2, somewhere between there, would be an x-intercept for this graph. So let's go ahead and evaluate these. First off, let's find f of -3. Well, if we do that, we're going to get 3 times -3 cubed minus 10 times -3 plus 9. And if we do that, that gives us out a -42, a negative number. But then if we also go ahead and evaluate f of -2, we're going to find that we're going to get, in this case, a positive 5. So that means here that since we have a -42 for the f of -3, but a positive 5 for an f of -2, there must be a real zero between -3 and -2. And so we see here that if we go ahead and plot f of -3, that would be at the point -3, -4, 2. And then if we also look at the point f of -2 equal to 5, that gives us the point -2, 5. We see that our graph is going to have to cross the x-axis somewhere between those points, and in fact it does. It looks to be about like -2.2 or something like that. But because of that change in sign going from the negative to the positive, that's the same thing as going from below the x-axis to above the x-axis, changing that sign, meaning that there has to be a real zero. One other rule that can help us with graphing polynomials is our rule for the turning points of a polynomial. In general, if f is a polynomial function of degree n, then the graph f is going to have at most n minus 1 turning points. So you think of it as a turning point as a change in direction. For example, if we think about the graph x squared, that means that since it's a quadratic, and it's degree 2, then that means it can only have one turning point. And if we think about a parabola, it indeed does only have one turning point. This right here is going to be our general step-by-step process, or a 5-step process for graphing polynomial functions. The very first thing we always want to do is use our leading coefficient test to determine the graph's end behavior. Step 2 then is to find the x-intercepts by setting the polynomial to 0, and then solving by finding its factors. And then for each of those factors, use those to find the zeros and to find out if it's going to cross or touch the x-axis based on its multiplicity. From there, we also want to find the y-intercept. But to find the y-intercept, we want to do this by plugging in 0 for the x value. We also talked about symmetry. In this case, if we know that the graph is going to have symmetry based on degree, then we can also use that to help us graph. But this step is not always necessary. The last thing we want to do is check to make sure that we actually graph the polynomial correctly by using our turning point rule. So remember that a graph can only have as many one less turning point than its degree. Let's practice this 5-step strategy to graph the polynomial 2 times x plus 2 squared times x minus 3. First thing we want to do is determine the end behavior. That means we need to identify the leading coefficient and the degree. Well, the degree here is going to be 3, since we have 2 x plus 2's and 1 x minus 3. So this means we're going to have a degree 3 polynomial. We also note here that the leading coefficient is that positive 2, which is out in front. And so since we have an odd degree and a positive leading coefficient, if we go back to our leading coefficient test, then this means that it's going to look like a normal cubic, which falls to the left and is going to rise to the right. You can think of that as a negative infinity to positive infinity. So that fall rise. Our next step here is to find the x-intercepts. We're going to think of that as the zeros of the function, and we can do this by setting the polynomial equal to 0. So if we go ahead and do that, we're going to plug in 0 for the f of x, and then we can go, since this is already in our factored form, we can go ahead and set those factors equal to 0. So if we set x plus 2 equal to 0, we're going to get x equal to a negative 2. And if we set the x minus 3 equal to 0, we're going to get out a positive 3. From there, then we want to see, well, since we know the zeros, we need to also know what their behavior is going to be at the x-axis. By this, we want to look at its multiplicity. Since the x plus 2 has a multiplicity of 2, that means it's even, which means it's going to touch at the x-axis. But since the x minus 3 only appears once, That means it's an odd multiplicity, and it's going to cross at positive 3. So now we know that it's going to touch at negative 2, but cross at a positive 3 on our graph. So we can go ahead and graph this part. So if we do that, we know that we're going to be touching at negative 2, but then crossing at a positive 3. And since we also know the end behavior, we know that we're going to fall to the left, but we also know we're going to rise to the right. So we're starting to get these pieces of our polynomial graph. The only part that we're missing right now is that in between. And that's going to be our next step. We can do this by finding out the y-intercept. Well, unlike finding the x-intercepts, where we're going to set it equal to 0, to find the y-intercept, we're going to plug in 0 for the x's. And so if we do that, we're going to get that 0 plus 2 squared times that 0 minus 3, which if we go ahead and simplify, is going to give us a y-intercept here of a negative 24. And so we can go ahead and add that to our graph. And so we know that the graph is going to go all the way down and cross the y-intercept, which is off the graph here at negative 24, but we're kind of getting this smooth, continuous shape of our polynomial. If we also look at this equation of this polynomial, we'll also know that there is not going to be any symmetry for this graph since we have no y-axis symmetry and no origin symmetry. The last thing we want to do is make sure that we actually graph this correctly. And so since this is a degree 3 polynomial, then that means at most we could have one less number of terms than that. So in this case, at most 2 terms. If we draw our graph one more time and look at what we did here, we have that y-intercept of that 0, negative 24 down there with our end behavior of the fall and the rise. And we also note that our graph only changes direction 2 times, which matches our rule. So this means that we have a pretty good idea that we have drawn this graph correctly. Please pause here, and we will do more examples of these in the next video.